All right, this will be Aerodynamics of Flight, Helicopter Handbook. Will be on page 17 of 28, Vertical Flight. Hovering is actually an element of vertical flight, increasing the angle of incidence of the rotor blades' pitch while keeping their rotation speed constant generates additional lift and the helicopter ascends. Decreasing the pitch causes the helicopter to descend. And in no wind condition in which lift and thrust are less than the weight and drag, the helicopter ascends vertically. If lift and thrust are greater than weight and drag, the helicopter ascends vertically. Forward flight. In steady forward flight with no change in airspeed or vertical speed, the four forces of lift, thrust, drag, and weight must be in balance. Once the tip path plane is tilted forward, the total lift thrust force is also tilted forward. The resultant lift thrust force can be resolved in two components: lift acting vertically upward and thrust acting horizontally in the direction of flight. In addition to lift and thrust, there is weight, the downward acting force, the drag, the force opposing motion of an airfoil through the air. In straight and level unaccelerated forward flight, straight and level flight is flight with a constant heading and at a constant altitude. Lift equals weight and thrust equals drag. If lift exceeds weight, the helicopter accelerates vertically until the forces are in balance. If thrust is less than drag, the helicopter slows down until the forces are in balance. As the helicopter moves forward, it begins to lose altitude because lift is lost as thrust is diverted forward. However, as a helicopter begins to accelerate from a hover, the rotor system becomes more efficient due to translational lift. The result is excess power over that which is required to hover. Continued acceleration causes an even larger increase in flow. To a point through the rotor disc, the more excess power. In order to maintain unaccelerated flight, the pilot must understand that with any changes in power or in cyclic movement, the helicopter begins either to climb or to descend. Once straight and level flight is obtained, the pilot should make note of the power torque setting required and not make major adjustments to the flight controls. Airflow and forward flight. Airflow across the rotor system in forward flight varies from airflow at a hover. In forward flight, airflow opposite the aircraft's flight path. The velocity of this airflow equals the helicopter's forward speed. Because the rotor blades turn in a circular pattern, the velocity airflow across a blade depends on the position of the blade and the plane of rotation at a given instant, its rotational velocity and airspeed of the helicopter. Therefore, the airflow meeting each blade varies continuously as the blade rotates. The highest velocity of the airflow occurs over the right side, the 3 o'clock position, of the helicopter's advancing blade in a rotor system that turns counterclockwise and decreases to a rotational velocity over the nose. It continues to decrease until the lowest velocity of the airflow occurs over the 9 o'clock position of the helicopter retreating blade. As the blade continues to rotate, the velocity of the airflow then increases to rotational velocity over the tail. It continues to increase until the blade is back at the 3 o'clock position. The advancing blade in figure 2-33 position A moves in the same direction as the helicopter. The velocity of the air meeting the blade equals rotational velocity of the blade plus wind velocity resulting from forward airspeed. The retreating blade, position C, moves in a flow of air moving in the opposite direction of the helicopter. The velocity of the airflow meeting this blade equals rotational velocity of the blade minus wind velocity resulting from forward airspeed. The blades, position B and D, over the nose and tail move essentially at right angles to the airflow created by forward airspeed. The velocity of airflow meeting these blades equals the rotational velocity. This results in a change to velocity of airflow all across the rotor disc and a change to the lift pattern of the rotor system. Look at pictures. So I'll have to look at these again later. For right now, we're just reading through. Advancing blade. As the relative wind speed of the advancing blade increases, the blade gains lift and begins to flap up. It reaches its maximum overlap velocity at 3 o'clock position, where the wind velocity is the greatest. This upflap creates a downward flow of air and has the same effect as increasing the induced flow velocity by imposing a downward vertical velocity vector to the relative wind, which decreases the angle of attack. Retreating blade. As relative wind speed of the retreating blade decreases, the blade loses lift and begins to flap down. It decreases at the maximum downward velocity at the 9 o'clock position, where wind velocity is the least. This downward flap creates an upward flow of air and has the same effect as decreasing the induced flow velocity by imposing an upward velocity vertical vector to relative wind, which increases angle of attack. Dissymmetry of lift. Dissymmetry of lift is the differential unequal lift between advancing and retreating halves of the rotor disc caused by different wind flow velocities across each half. This difference in lift would cause the helicopter to be uncontrollable in any situations other than hovering in a calm wind. There must be a means of compensating, correcting, or eliminating this unequal lift to maintain symmetry of lift. When the helicopter moves through the air, the relative airflow through the main rotor disc is different on the advancing side than on the retreating side. The relative wind encountered by the advancing blade is increased by the forward speed of the helicopter, while the relative wind speed acting on the retreating blade is reduced by the helicopter's forward speed. Therefore, as a result of the relative wind speed, the advancing blade side of the rotor disc can produce more lift than the retreating blade side. Figure 2-34. The blade tip speed of this helicopter is approximately 400 knots. If the helicopter is moving forward at 100 knots, the relative wind speed on the advancing side is 400 knots. On the retreating side, it's only 200 knots. The difference in speed causes a dissymmetry of lift. That is a picture. And we're going to go on. If this condition were allowed to exist, a helicopter with a counterclockwise main rotor blade rotation would roll to the left because of this difference in lift. Yeah, not much lift on the left, a lot of lift on the right. In reality, the main rotor blades flap and feather automatically to equalize lift across the rotor disc. Articulated rotor systems, usually with 3 or more blades, incorporate a horizontal hinge, flapping hinge, to allow the individual rotor blades to move or flap up and down as they rotate. A semi-rigid rotor system, 2 blades, utilizes the teetering hinge, which allows the blades to flap as a unit. When one blade flaps up, the other flaps down. As shown in figure 2-35, the rotor blade reaches the advancing side of the rotor disc A. It reaches its maximum flap velocity. When the blade flaps upward, the angle between the chord line and the resultant relative wind decreases. This decreases the angle of attack, which reduces the amount of lift produced by the blade. At position C, the rotor blade is now at its maximum down flapping velocity. Due to down flapping, the angle between the chord line and the resultant relative wind increases. This increases the angle of attack and thus the amount of lift produced by the blade. The combination of blade flapping and slow relative wind acting on the retreating blade normally limits the maximum forward speed of a helicopter. At a high forward speed, the retreating blade stalls because of the high angle of attack and slow relative wind speed. This situation is called retreating blade stall and is evidenced by a nose pitch up, vibration, and rolling tendency, usually to the left in helicopter with counterclockwise blade rotation. Pilots can avoid retreating blade stall by not exceeding the never exceed speed. This speed is designated V, big V with an NE, and is indicated on a placard and marked on the airspeed indicator by a red line. Blade flapping compensates for dissymmetry of lift in the following way. At a hover, equal lift is produced around the rotor system with equal pitch, AOI, on all the blades and at all points in the rotor system, disregarded compensation for translating tendency. The rotor disc is parallel to the horizon. To develop a thrust force, the rotor system must be tilted in the desired direction of movement. Cyclic feathering changes the angle of incidence differentially around the rotor system. Forward cyclic movements decrease the angle of incidence at one part of the rotor system while increasing the angle in another part. When transitioning to forward flight, either from a hover or taking off from the ground, pilots must be aware that as the helicopter speed increases, transitional lift becomes more effective and causes the nose to rise up or pitch up, sometimes referred to as blowback. This tendency is caused by the combined effects of dissymmetry of lift and transverse flow. Pilots must correct for this tendency to maintain a constant rotor disc attitude that will move the helicopter through the speed range in which blowback occurs. If the nose is permitted to pitch up while passing through this speed range, the aircraft may also tend to roll to the right. To correct for this tendency, the pilot must continuously move the cyclic forward as velocity of the helicopter increases until the takeoff is complete and the helicopter has transitioned into forward flight. Figure 3-26 illustrates the changes in pitch angles as the cyclic is moved forward at increased airspeeds. At a hover, the cyclic is centered and the pitch angle of the advancing and retreating blades is the same. At low forward speeds, moving the cyclic forward reduces pitch angle of the advancing blade and increases pitch angle of the retreating blade. This causes a slight rotor tilt. At higher forward speeds, the pilots must continue to move the cyclic forward. This further reduces pitch angle of the advancing blade and further increases pitch angle of the retreating blade. As a result, there is even more tilt to the rotor than at lower speeds. A horizontal lift component, the thrust, generates higher helicopter airspeed. The higher airspeed induces blade flapping to maintain symmetry of lift. The combination of flapping and cyclic feathering maintains symmetry of lift and desired attitude on the rotor system and helicopter. All right, so that was page 19 of 28 pretty much. Yep, page 18 and 19 of 28. We're going to go into 20. All right, take care.